there is something about the ocean at night that feels different, not just visually, but conceptually. When the surface goes dark and the horizon disappears, it becomes easier to imagine just how little we actually understand about what lies beneath. Because despite satellites mapping distant planets, despite telescopes peering into galaxies billions of light years away, the deep ocean, right here on Earth, remains one of the least explored places we have ever encountered. And that's where tonight's journey begins, somewhere between what we know and what we might be missing. Before we go any further, if you enjoy this kind of slow, thoughtful exploration, the kind that doesn't rush to conclusions, but instead follows the evidence wherever it leads, consider subscribing to the channel. And let me know in the comments where you're listening from tonight, whether you're near the coast, in a city far from the sea, or somewhere in between. It's always interesting to see how far these quiet, late-night conversations travel. Now, when most people think about the ocean, they imagine the surface, waves, sunlight, maybe coral reefs or schools of fish. But that surface layer is almost irrelevant when compared to the sheer scale of what lies below. The ocean's average depth is about 3.7 kilometers, and in some places, like the Mariana Trench, it plunges to nearly 11 kilometers. To put that into perspective, if Mount Everest were placed at the bottom of that trench, its peak would still be more than a kilometer underwater. And yet, despite that scale, more than 80% of the ocean remains unmapped, unobserved, and unexplored. The mainstream explanation for this is fairly straightforward. The deep ocean is an incredibly hostile environment. There is no sunlight beyond a certain depth. Temperatures hover just above freezing, and the pressure is immense, hundreds of times greater than what we experience at the surface. Technology struggles under these conditions. Submersibles are expensive, fragile, and limited in how long they can operate. Communication becomes difficult. Navigation becomes uncertain. So, from a practical standpoint, it makes sense that exploration has been slow. But here's where things begin to get interesting. Because while the difficulty explains why we haven't explored much of the deep ocean, it doesn't fully explain what we have found when we do manage to reach those depths. And more importantly, it doesn't explain some of the patterns that keep appearing, quietly, across decades of research. Take bioluminescence, for example. In the absence of sunlight, many deep-sea organisms produce their own light. This is well documented, well studied. Fish, jellyfish, and even bacteria emit soft glows, flashes, or pulses of light for communication, camouflage, or hunting. The mainstream view is that this is simply an evolutionary adaptation, a clever solution to the problem of darkness. And that makes sense. But when researchers began cataloging these light patterns more closely, they noticed something curious. The distribution and behavior of bioluminescent organisms aren't random. In certain regions, especially at specific depths, the lights appear in coordinated bursts, almost like signals. Not quite structured enough to be called communication in the way we understand it, but not entirely chaotic either. It raises a quiet question. Are we seeing individual organisms acting independently, or something more coordinated that we don't yet fully recognize? And that question leads into a broader pattern, because the deep ocean is full of these almost explained phenomena. Sounds that don't quite match known sources. Movements that don't align with established migration patterns. Structures on the seafloor that appear geometric, but are often dismissed as natural formations shaped by currents and geological processes. For instance, there have been sonar readings over the years that suggest large moving objects at extreme depths. The mainstream explanation typically attributes these to schools of fish, unknown species, or even equipment anomalies. And again, those are reasonable explanations. Sonar is not perfect. The ocean is full of life we haven't catalogued yet. But what makes these readings interesting is their consistency. Similar patterns have been recorded in different parts of the world, across different decades, using different technologies. It doesn't prove anything on its own, but it does suggest that there may be behaviors or entities in the deep ocean that we don't yet fully understand, not because they are necessarily extraordinary, but because we've only seen fragments of them. Then there's the question of underwater geography. We tend to imagine the ocean floor as a relatively smooth, muddy expanse, punctuated by trenches and ridges. But in reality, it's far more complex. There are vast mountain ranges, deep valleys, and hydrothermal vent systems that release superheated water rich in minerals. Around these vents, entire ecosystems thrive, completely independent of sunlight, relying instead on chemical energy. This discovery alone reshaped how scientists think about life, not just on Earth, but potentially on other planets. If life can exist in total darkness, sustained by chemical reactions rather than sunlight, then the possibilities expand dramatically. Moons like Europa or Enceladus, with their subsurface oceans, suddenly seem less inhospitable. But even here, there are details that don't quite fit neatly into our expectations. Some vent ecosystems appear to develop and stabilize faster than models predict. Certain species exhibit resilience to temperature and pressure changes that seem almost excessive, given their environment. It's not that these observations contradict known science, but they stretch it, hinting that there are underlying mechanisms we haven't fully identified. And then there's perhaps one of the most quietly unsettling aspects of deep ocean research. How often we encounter things that are described as unidentified, not in a dramatic sense, but in a very literal scientific one. Creatures that don't fit existing classifications, behaviors that don't match known patterns, signals that don't correspond to known sources. The default response, understandably, is caution. Scientists avoid jumping to conclusions. Unknown does not mean mysterious in a sensational way. It simply means not yet understood. And that's an important distinction. But if you step back and look at the bigger picture, a pattern begins to emerge. The deep ocean isn't just unexplored, it's consistently producing observations that challenge our assumptions, even within the limited areas we've studied. So the question becomes less about any single phenomenon, and more about the overall structure of what we know. If the small percentage of the ocean we've explored already contains this many uncertainties, what does that imply about the remaining majority? One way to approach this is to consider how exploration tends to work historically. When humans first mapped continents, early maps were filled with gaps, approximations, and sometimes outright errors. Over time, those maps became more accurate, but the process wasn't linear. New discoveries often forced revisions of previous assumptions. Coastlines shifted. Mountain ranges were redefined. Entire regions were reinterpreted. It's possible that we're in a similar phase with the deep ocean. What we currently see as isolated anomalies might eventually fit into a broader, coherent understanding. But it's also possible that some of these anomalies represent entirely new categories of phenomena, things that don't just fill gaps in our knowledge, but expand the framework itself. And that brings us to a more speculative, but still grounded question. Not whether there is something hidden in the deep ocean in a dramatic or fantastical sense, but whether our current methods and assumptions are sufficient to fully understand it. Are we asking the right questions? Are we interpreting the data in the most useful way? Or are we, in some cases, seeing only what we expect to see and overlooking patterns that don't fit neatly into existing models? Because the deep ocean, by its very nature, resists easy observation. It's not just dark, it's isolating. It separates us from direct experience. Most of what we know comes through instruments, sensors, and brief glimpses captured by submersibles. And while those tools are incredibly advanced, they still represent a kind of translation, a filtered version of reality. So as we move deeper into this series, the goal isn't to jump to conclusions or to suggest that there are hidden truths waiting to be uncovered in a dramatic sense. Instead, it's to carefully examine what we do know, to notice where the patterns don't quite align, and to explore the possibility that the deep ocean might be more complex and perhaps more interconnected than we currently understand. Because sometimes, the most interesting discoveries don't come from finding something completely new, but from looking at familiar data in a slightly different way. And with that in mind, we'll begin to move deeper, not just in terms of depth, but in terms of detail, as we start to examine specific regions, specific phenomena, and the subtle inconsistencies that make the deep ocean one of the most intriguing frontiers we have left. As we move deeper into this, it helps to slow down and focus not on the entire ocean at once, but on specific layers. Because the ocean is not a single uniform environment. It is structured, almost like an invisible landscape stacked vertically, each layer with its own rules, its own pressures, its own forms of life. And what's interesting is that many of the patterns and inconsistencies we touched on earlier begin to make more sense, or in some cases, less sense, when you look at where they occur within these layers. The uppermost zone, where sunlight still penetrates, is relatively well understood. Photosynthesis happens here. Food chains are familiar. But once you descend beyond roughly 200 meters, you enter what's known as the twilight zone, or the mesopelagic layer. Light fades rapidly, but it doesn't disappear entirely. It's dim, scattered, unstable. And in this region, something subtle but important begins to happen. Organisms start to rely less on vision in the conventional sense, and more on alternative ways of sensing their environment. Pressure changes, chemical signals, faint vibrations. The mainstream explanation for this shift is straightforward. As light disappears, evolution favors other senses. That's expected. But the twilight zone also hosts one of the largest migrations on Earth, something called the DL vertical migration. Every night, billions of organisms rise toward the surface to feed, and every day, they descend back into the darkness. This movement is so vast that it was once mistaken for the ocean floor on early sonar systems. At first glance, this seems like a well-understood ecological cycle. Predators follow prey follow food sources, and the timing is driven by light levels. But when researchers began examining this migration more closely, they noticed inconsistencies. The timing isn't always perfectly aligned with sunset or sunrise. In some regions, the movement begins earlier than expected or continues later. In others, certain species deviate from the pattern entirely. The usual explanation is that local conditions, temperature, predator presence, water chemistry, affect behavior. And that's reasonable. But when you step back and compare data across different oceans, a more subtle question emerges. If this migration is primarily driven by light, why does it sometimes behave as though it's responding to something else? Something less obvious, less directly measurable. It's not a dramatic inconsistency, but it's persistent enough to raise curiosity, especially when you consider that this migration involves organisms with relatively simple nervous systems. The coordination required is immense, yet the mechanism behind that coordination is not fully understood. Is it purely individual responses adding up to a collective pattern? Or is there some form of environmental signaling that synchronizes behavior on a larger scale? And this brings us to a recurring theme in deep ocean research: the difference between individual explanation and system-level behavior. We often explain phenomena by breaking them down into smaller parts, This species does this. That species reacts in that way. But sometimes, when you look at the system as a whole, the behavior seems too coordinated, too consistent across large areas, to be entirely random or purely local. As we descend further into the bathypelagic zone, light disappears completely. This is true darkness, not the kind we experience on land, where there's always some ambient glow, but an absence of light so complete that vision, in the way we understand it, becomes almost irrelevant. And yet, life continues here, not just surviving, but adapting in ways that are, in some cases, difficult to predict. One of the more well-known adaptations is the use of bioluminescence, which we touched on earlier. But in this deeper context, it takes on new complexity. Some organisms use light as bait, others as a form of communication, and some as a defensive mechanism. The patterns vary widely: flashes, pulses, slow glows, sudden bursts. The mainstream interpretation is that each of these patterns evolved independently, shaped by specific ecological pressures. But when researchers map these behaviors across different species and regions, they sometimes find similarities that aren't easily explained by shared ancestry or environment. It's as if certain designs of light behavior reappear in unrelated organisms. Again, this doesn't imply anything extraordinary. Convergent evolution, where different species develop similar traits independently, is a well-established concept. But the deep ocean provides an environment so isolated and extreme that it raises an interesting question. How many of these similarities are truly independent, and how many might be influenced by factors we haven't fully identified? Then there are the sounds. The deep ocean is not silent, despite what we might imagine. Hydrophones, underwater microphones, have recorded a wide range of acoustic phenomena. Some are clearly understood: whale calls, geological activity, the movement of water masses. But others are less clear. Over the years, certain sounds have been recorded that don't match known sources. They are often given informal names: the bloop, the Julia, the upsweep. In most cases, scientists eventually find plausible explanations, often related to ice movement or underwater geological processes. And that's important. It shows that the scientific method works, that unknowns can become known over time. But what's interesting is not any single sound. It's the pattern of how often these unexplained signals appear before being understood, and how similar they sometimes seem to each other, even when recorded in different locations. It suggests that there are processes occurring in the deep ocean that we are only intermittently able to detect and only partially able to interpret. And this leads to a broader consideration. The tools we use to study the ocean, sonar, hydrophones, remote-operated vehicles, are incredibly advanced, but they are still limited. They capture fragments of a much larger system, and when those fragments don't align perfectly with our expectations, we tend to either refine our models or, in some cases, set aside the anomaly until more data is available. That's a practical approach, but it also means that there may be patterns hidden within those anomalies, connections that only become visible when viewed collectively rather than individually. As we go deeper still, approaching the abyssal plains, the environment becomes even more stable, at least on the surface. Temperatures are consistent, movement is slow, and life appears sparse. But this apparent simplicity can be misleading. Because even in these vast, quiet regions, there are signs of structure, both biological and geological, that challenge our assumptions. For example, the seafloor is not uniformly covered in sediment. In some areas, there are formations that appear almost patterned: lines, clusters, repeating shapes. The mainstream explanation is that these are the result of currents, chemical processes, or the activity of organisms interacting with the sediment over time. And that explanation holds in many cases. But there are instances where the patterns are more regular than expected, or occur in environments where the usual shaping forces are minimal. It's not that they defy explanation, but they invite closer examination. Because when patterns appear in nature, especially in environments that are difficult to observe directly, they often point to underlying processes that we don't fully understand yet. And the deep ocean, more than almost any other environment on Earth, is full of these quiet, persistent patterns. So as we continue this exploration, the focus will gradually shift from broad observations to more specific cases, individual discoveries, particular regions, and the subtle inconsistencies that make them worth paying attention to. Not because they necessarily indicate something hidden in a dramatic sense, but because they remind us that our understanding is still evolving. And perhaps that's the most important perspective to carry forward. Not the expectation of uncovering something extraordinary, but the willingness to look carefully at what's already there, and to notice where the details don't quite fit. Because in a place as vast and as unexplored as the deep ocean, those small mismatches can sometimes lead to the most meaningful insights. If we continue descending, past even the slow, drifting calm of the abyssal plains, we eventually reach environments that feel less like an extension of the ocean and more like entirely separate worlds. Places where the rules shift again, not gradually, but abruptly. These are the Hadal zones, deep ocean trenches that cut into the Earth's crust like narrow scars, some plunging deeper than anything else on the planet. And it's here, in these isolated and extreme environments, that some of the most quietly puzzling observations begin to take shape. The mainstream understanding of ocean trenches is rooted in geology. They form where tectonic plates converge, one sliding beneath another in a process called subduction. Over millions of years, this creates long, steep depressions in the seafloor, often thousands of kilometers in length, but only tens of kilometers wide. The Mariana Trench is the most well-known example, but there are many others scattered across the globe, each with its own characteristics, depths, and geological activity. From a scientific perspective, trenches are valuable because they offer a glimpse into Earth's internal processes. Sediment accumulates here, sometimes preserving chemical records of past events. Geological activity can be studied in relative isolation. And despite the immense pressure, more than 1,000 times what we experience at the surface, life still exists. That alone is worth pausing on. Because for a long time, it was assumed that such depths would be largely barren. The pressure, the cold, the absence of light, it seemed like too much for complex ecosystems to sustain themselves. But as exploration improved, researchers began finding organisms not just surviving, but adapting in ways that challenge earlier assumptions. Amphipods, for example, small, shrimp-like creatures, have been observed at depths exceeding 10,000 meters. Certain species of snailfish appear to thrive in these conditions, their bodies adapted to withstand pressures that would collapse most known biological structures. The mainstream explanation focuses on biochemical adaptations, flexible cell membranes, pressure-resistant proteins, and metabolic processes that function efficiently in extreme environments. And yet, even within this framework, there are questions. Some of these organisms exhibit traits that seem, in a sense, over-engineered for their environment. Not in a mysterious way, but in a way that suggests there may be additional pressures or variables influencing their evolution that we don't fully account for. It's one thing to adapt to high pressure. It's another to do so with a level of specialization that appears to exceed what we would predict based on known conditions alone. Then there's the question of isolation. Trenches are often described as being like islands, but inverted, cut off from surrounding ecosystems by depth and topography. This isolation should, in theory, lead to highly localized evolutionary paths, with species developing unique traits specific to their trench. And that does happen. But what's interesting is that in some cases, similar species, or at least very similar adaptations, appear in trenches that are geographically distant from each other, with no obvious connection. The mainstream explanation is that these traits evolved independently, driven by similar environmental pressures. Again, convergent evolution. But as with bioluminescence patterns in earlier layers, the repetition of similar solutions across isolated environments raises a subtle question. Are these systems truly as isolated as we think, or are there forms of connectivity, perhaps through deep ocean currents, or as yet unmapped pathways, that allow for more interaction than our current models suggest? And this is where the physical structure of the deep ocean becomes particularly relevant. Because while we often think of trenches as separate, disconnected features, the ocean floor itself is part of a vast, interconnected network. Ridges, slopes, plains and trenches all exist within a dynamic system shaped by currents that move not just horizontally, but vertically as well. These deep currents are slow, almost imperceptible, but they operate on timescales that are difficult to intuit. Water masses can take centuries to circulate through the deepest parts of the ocean. During that time, they carry not just heat and chemicals, but potentially biological material as well. Microorganisms, organic particles, even larvae. So, while a trench may appear isolated in the short term, over longer timescales, it may be part of a much larger system of exchange. And if that's the case, then some of the similarities we observe between distant ecosystems might not be entirely independent after all. They could be connected through processes that are simply too slow or too subtle for us to easily detect. Then there's another layer to this, something less tangible, but still grounded in observation. Because when submersibles descend into these trenches, researchers often describe a certain stillness. Not just the absence of movement, but a kind of environmental stability that feels different from shallower regions. It's not empty, but it's quiet in a way that's difficult to fully capture through instruments. From a scientific standpoint, this makes sense. There is little turbulence at these depths. Currents are slow. External influences are minimal. But within that stillness, there are occasional anomalies, sudden movements, unexpected readings, brief appearances of organisms that don't match known classifications. These are usually treated cautiously, as they should be. Data at these depths can be noisy. Equipment can behave unpredictably under extreme pressure. And the last thing researchers want is to misinterpret an artifact as a discovery. So most anomalies are catalogued, noted, and set aside until further evidence can confirm or clarify them. But over time, as more dives are conducted, a pattern begins to emerge. Not of specific anomalies repeating exactly, but of a consistent presence of the unexpected. It's almost as if the deeper we go, the less complete our models become, not because they are wrong, but because they are built on limited data. And this leads to a broader question about exploration itself. When we explore environments that are difficult to access, our understanding tends to develop in fragments. We gather data points, build models, test hypotheses. But those models are only as good as the data we have, and in the deep ocean, that data is sparse. So when something doesn't fit, we have a choice. We can adjust the model, or we can assume the anomaly will eventually be explained within the existing framework. Most of the time, the second approach works, but not always immediately. And sometimes, the delay between observation and explanation can reveal something important, not necessarily about the anomaly itself, but about the limits of our current understanding. And perhaps that's where the deep ocean becomes most interesting. Not as a place of hidden secrets in the traditional sense, but as a place where the boundaries of our knowledge are more visible, where the gaps are easier to notice, because the environment resists easy observation. So as we continue this descent, both literally and conceptually, the focus will shift again. From the structure of the ocean and its ecosystems, to the tools we use to explore them, and the ways in which those tools might shape what we see, what we miss, and how we interpret the signals coming back from the depths. Because sometimes, understanding the unknown isn't just about looking deeper, it's about examining how we're looking in the first place. As we begin to look more closely at how we explore the deep ocean, something subtle starts to emerge. A realization that what we perceive down there is not a direct experience, but a translation. Every image, every sound, every data point that reaches us from those depths has already passed through layers of interpretation. Machines converting pressure into signals, software reconstructing shapes from echoes, cameras adjusting to near total darkness. And while these tools are remarkably advanced, they are not neutral. They shape the way the deep ocean is revealed to us. The most commonly used method for mapping the seafloor is sonar. At its core, it's a simple idea. Emit a sound wave, measure how long it takes to bounce back, and use that information to infer distance and shape. Over time, this process builds detailed maps of underwater terrain. It's efficient, scalable, and essential for exploring areas that are too deep or vast for direct observation. The mainstream understanding is that modern sonar systems are highly accurate, capable of resolving features down to surprisingly fine detail. And that's true within certain limits. But those limits are important. Because sonar doesn't see objects in the way we see them, it interprets reflections. It reconstructs shapes based on how sound waves interact with surfaces. And in complex environments, those reflections can become ambiguous. For example, soft sediment absorbs sound differently than hard rock. Biological material, like dense schools of fish or drifting organic matter, can scatter sound in unpredictable ways. Even temperature gradients in the water can bend sound waves, slightly altering their paths. Each of these factors introduces small uncertainties. Individually, they're manageable, but when combined, especially in deep and irregular terrain, they can produce images that are less precise than they appear. This doesn't mean sonar maps are unreliable. Far from it. They are incredibly useful and generally accurate representations of large-scale features. But it does mean that at smaller scales, or in areas with unusual conditions, what we're seeing is a best approximation, not a perfect reconstruction. And this becomes particularly relevant when we encounter features that seem unexpected, structures that appear unusually regular, or formations that don't immediately align with known geological processes. The default assumption is that these are natural, shaped by currents, sediment flow, or tectonic activity. And in most cases, that's likely correct. But the interesting part is how quickly we move from observation to explanation. A shape appears geometric, we attribute it to natural forces, and the question is considered resolved. Yet the process by which that shape was formed is not always fully understood. It's inferred based on what we know about similar environments. And that leaves a small but important gap between what we see and how we explain it. Then there are submersibles, both manned and remotely operated vehicles. These provide something closer to direct observation. Cameras capture footage, robotic arms collect samples, sensors record environmental data in real time. Compared to sonar, this feels more immediate, more tangible. But even here, there are limitations that are easy to overlook. visibility in the deep ocean is often extremely limited. Particles in the water scatter light, creating a kind of visual noise. Artificial lighting, necessary for any kind of imaging, only illuminates a small area, leaving everything beyond it in darkness. Depth perception becomes difficult. Scale can be misleading. In some recordings, objects appear larger or closer than they actually are. Movement seems slower or faster depending on how the camera is positioned. And when something unfamiliar enters the frame, an organism with an unusual shape or motion, it can be difficult to interpret what we're actually seeing. The mainstream approach to this is careful analysis. Footage is reviewed, compared with known species, cross-referenced with environmental data. Over time, many of these unknowns are identified, but not all of them. Some remain ambiguous, not because they are necessarily extraordinary, but because the data isn't clear enough to draw a definitive conclusion. And this brings us to an interesting intersection between technology and perception. Because when we explore environments that are fundamentally inaccessible to our senses, we rely entirely on tools to interpret them. And those tools, no matter how advanced, introduce a layer of abstraction. It's a bit like trying to understand a landscape by looking at it through a narrow window, with filters that adjust the light and shape the view. You can still learn a great deal. You can map the terrain, identify patterns, build models. But there will always be aspects that remain just out of reach, not because they are hidden, but because the way we're observing them isn't fully aligned with their nature. This becomes even more apparent when we consider how data is processed after it's collected. Raw data from deep-sea exploration is often incomplete or noisy. It needs to be cleaned, filtered, interpreted. Algorithms fill in gaps, smooth out irregularities, and generate coherent images or models. Again, this is necessary. Without it, the data would be too chaotic to use. But it also means that what we end up seeing is not just the ocean. It's the ocean as interpreted through a series of decisions about how to handle uncertainty. And most of the time, those decisions are based on well-established principles. They are grounded in physics, validated through testing, refined over years of use. But in edge cases, situations where the data doesn't quite fit expectations, those same processes can sometimes obscure as much as they reveal. For instance, if a sonar return is inconsistent with known patterns, it might be smoothed out or categorized as noise. If a visual anomaly appears in footage, it might be dismissed as a lighting artifact or a passing object outside the focal range. These are reasonable assumptions. They prevent false positives, maintain scientific rigor, but they also raise a subtle question. How often might something genuinely unusual be filtered out? Not because it's impossible, but because it doesn't fit within the parameters we've defined for what is likely. This is not a criticism of the scientific process. It's a reflection of its constraints. Science operates by building models based on available evidence, and those models are constantly refined. But in environments where evidence is sparse and difficult to obtain, the refinement process can take a long time. And during that time, certain observations may remain in a kind of limbo, recorded, but not fully integrated into our understanding. So as we continue to explore the deep ocean, it becomes important not just to look at what we found, but to consider how we found it. To recognize that our view of the depths is mediated, shaped by tools that are powerful, but not perfect. Because once you start to see that layer of interpretation, it changes how you think about everything else. Patterns become a little less certain. Explanations become a little more tentative. And the space between what we observe and what we understand becomes just a bit more visible. And in that space, there is room for careful curiosity, Not the kind that jumps to conclusions, but the kind that asks quiet, persistent questions. The kind that notices when something doesn't quite align and chooses to look a little closer. Because the deeper we go, the more that space seems to expand, and the more important it becomes to understand not just the ocean itself, but the lens through which we're trying to see it. As we continue moving deeper into this quiet examination, it becomes useful to shift focus again, this time towards something less visible, but perhaps even more revealing than what we can see or map: the chemistry of the deep ocean. Because beneath the darkness, beyond the pressure and the silence, there is an ongoing exchange of elements, a slow but constant reshaping of the environment at a molecular level. And it's here, in these unseen processes, that some of the more subtle inconsistencies begin to appear. The mainstream understanding of deep ocean chemistry is grounded in well-established cycles: carbon, nitrogen, sulfur. These elements move through the ocean in predictable ways, driven by biological activity, geological processes, and the gradual mixing of water masses. Organic material from the surface sinks slowly, feeding deep-sea ecosystems in what is often described as marine snow. Over time, this material is broken down, recycled, or buried in sediments. It's a system that, on the surface, appears balanced. Inputs and outputs are accounted for. Models track how much carbon is absorbed by the ocean, how nutrients circulate, how ecosystems sustain themselves despite the lack of sunlight. And for the most part, these models work. They explain a great deal about how the ocean functions as a global system. But when researchers take precise measurements in specific deep-sea environments, they sometimes encounter results that don't quite match expectations. Certain chemical concentrations are higher or lower than predicted. Rates of decomposition vary more than models suggest they should. In some regions, the amount of organic material reaching the seafloor appears insufficient to support the observed levels of biological activity. The usual explanations involve local variability. Perhaps there are unaccounted sources of nutrients, underwater currents bringing in additional material, or geological activity releasing chemicals from beneath the seafloor. These are plausible, and in many cases, likely correct. But when similar discrepancies appear in different locations, under different conditions, it raises a broader question. Are our models missing something fundamental about how these systems operate? Not in a dramatic sense, but in the accumulation of small assumptions that, when combined, leave gaps in our understanding. One area where this becomes particularly interesting is around hydrothermal vents. These are regions where seawater seeps into the Earth's crust, becomes superheated by underlying magma, and then rises back up, carrying dissolved minerals with it. The result is a kind of underwater plume, rich in chemicals like hydrogen sulfide, which can be used as an energy source by certain microorganisms. The discovery of these vent ecosystems was a turning point in ocean science. It showed that life could exist independently of sunlight, relying instead on chemosynthesis. Microbes convert chemical energy into organic matter, forming the base of a food chain that includes larger organisms like tube worms, clams, and crustaceans. The mainstream explanation is that these ecosystems are localized, dependent on the specific conditions around each vent. And that's largely true. But what's intriguing is how quickly some of these ecosystems appear to establish themselves after a new vent forms. In some cases, within a relatively short period, geologically speaking, complex communities emerge, with multiple species interacting in stable ways. This rapid development suggests that either these organisms are highly efficient at colonizing new environments, or that the necessary components for these ecosystems are more widespread than we currently assume. Perhaps microbial life capable of exploiting these chemical gradients is already present throughout the deep ocean, waiting for the right conditions to become active. And that idea leads into another subtle pattern. Because when scientists analyze water samples from different depths and regions, they often find traces of microbial life that don't correspond neatly to the surrounding environment. Organisms appear in places where they aren't actively thriving, but are still present in low concentrations. The standard interpretation is that these microbes are being transported by currents, drifting passively until they encounter suitable conditions. But if that's the case, it implies a kind of underlying connectivity, a microbial network that spans vast distances, linking different parts of the ocean in ways that are not immediately visible. And if such a network exists, even at a microscopic level, it could have implications for how we understand larger-scale patterns. Chemical cycles, biological activity, even the formation of certain structures on the seafloor might be influenced by processes that operate across these hidden connections. Then there's the question of time. The deep ocean moves slowly, not just in terms of currents, but in terms of change. Chemical processes can take years, decades, even centuries to unfold. Water that sinks in one part of the world may not resurface for hundreds of years, carrying with it a chemical signature from a different era. This means that when we take a measurement in the deep ocean, we are not just observing a location, we are observing a moment in a long, ongoing process. And if that process is not fully understood, then the data we collect may be more complex than it appears. For example, certain deep-sea sediments contain layers that record past environmental conditions, variations in temperature, chemical composition, biological activity. These records are invaluable for understanding Earth's history, but they also reveal periods where conditions changed more rapidly or more dramatically than expected. The mainstream explanations often involve shifts in climate, volcanic activity, or changes in ocean circulation. And again, these are well supported, but the precise mechanisms, especially at smaller scales, are not always clear. There are moments in the record where the cause and effect relationship is not fully resolved. And that brings us back to a familiar theme: the idea that the deep ocean is not just unexplored in a spatial sense, but in a temporal one as well. It holds records of processes that operate on timescales far beyond our everyday experience. And within those records, there are details that don't always align perfectly with our current models. So as we consider the chemistry of the deep ocean, it becomes less about individual anomalies and more about the overall structure of the system. A system that is vast, interconnected, and operating across multiple scales of time and space. And within that system, there are small inconsistencies, differences between what we expect and what we observe. Not large enough to overturn our understanding, but persistent enough to suggest that there is still more to learn. So the question becomes not whether the deep ocean is hiding something in a dramatic sense, but whether it is quietly operating in ways that are more complex than our current frameworks can fully capture. And as we move forward, we'll begin to explore another dimension of this complexity: the interaction between the deep ocean and forces that extend beyond it, gravitational influences, electromagnetic fields, and the subtle ways in which the ocean might be connected to processes that we usually think of as separate from it. Because sometimes, understanding a system requires looking not just at what's inside it, but at how it interacts with everything around it. As we continue to widen the frame just slightly, the deep ocean begins to feel less like an isolated environment and more like a system that is constantly interacting with forces we don't usually associate with it. Not in an abstract way, but in very real, measurable ways, through gravity, through planetary motion, through electromagnetic influences that, while subtle, are always present. And what's interesting is not that these forces exist, we expect them to, but how their effects sometimes appear more complex than the models we use to describe them. Take tides, for example. On the surface, tides are familiar, predictable, driven primarily by the gravitational interaction between the Earth, the Moon, and to a lesser extent, the Sun. The mainstream explanation is well understood. Water bulges slightly toward the Moon due to gravitational pull, and as the Earth rotates, this creates the rising and falling of sea levels we observe along coastlines. But tides don't only affect the surface. They extend throughout the entire ocean, including its deepest layers. In fact, in some parts of the deep ocean, tidal forces interact with underwater topography, ridges, slopes, trenches, in ways that generate internal waves. These are not waves you can see, but massive movements of water that travel along density boundaries, sometimes hundreds of meters tall, moving slowly through the darkness. From a scientific standpoint, internal waves are a known phenomenon. They play a role in mixing ocean layers, distributing heat and nutrients. But what's intriguing is how little we directly observe them compared to their estimated scale. Most of what we know comes from indirect measurements, changes in temperature, pressure, or current speed detected by instruments placed in specific locations. And when these measurements are analyzed, the patterns don't always align perfectly with what models predict. The timing, the intensity, the propagation of these waves can vary in ways that suggest additional influences. Perhaps subtle interactions between tidal forces, seafloor geometry, and long-term ocean circulation patterns that are not yet fully integrated into our understanding. Then, there's the Earth's magnetic field. It surrounds the planet, extending from the core out into space, and it interacts continuously with solar radiation. At the surface, we experience it primarily through compasses, or occasionally auroras near the poles. But beneath the ocean, especially at great depths, its presence is quieter, less obvious. Still, it's there, and certain marine organisms are known to sense it. Some species of fish, and even microorganisms, appear to use the Earth's magnetic field for navigation. The mainstream explanation is that they possess specialized biological structures that allow them to detect magnetic variations, helping them orient themselves over long distances. That in itself is fascinating, but it also raises a subtle question when we consider the deep ocean. In an environment where visual cues are minimal or non-existent, and where chemical signals can disperse slowly, the ability to detect magnetic fields could provide a form of spatial awareness that we don't fully appreciate. Now, there's no evidence suggesting anything unusual about this process. It's a natural adaptation. But when you combine it with the vast, interconnected nature of the ocean, it invites a broader line of thinking. Could there be layers of environmental information, magnetic, gravitational, chemical, that organisms are responding to in ways that create patterns we don't immediately recognize? Because when we observe behavior, migration, clustering, synchronized movement, we often interpret it through the lens of visible or measurable factors. Light levels, temperature gradients, food availability. But if there are additional influences, subtle but consistent, they might shape behavior in ways that are harder to detect. And then there's something even more abstract, but still grounded in observation: resonance. Not in a dramatic sense, but in the way systems can respond to repeated forces over time. The ocean, with its vast mass and layered structure, is constantly being influenced by periodic forces, tidal cycles, planetary rotation, even seasonal variations. Over long periods, these repeated influences can create patterns, oscillations, cycles, feedback loops. Some of these are well understood, like the thermohaline circulation, sometimes referred to as the global conveyor belt, where differences in temperature and salinity drive large-scale movement of water around the planet. But within these larger systems, there are smaller oscillations that are less clearly defined. Variations that don't fit neatly into established cycles, or that appear to shift over time without a clear external trigger. These are often attributed to the complexity of the system. Too many variables interacting to produce perfectly predictable outcomes. And that's likely true. But it also highlights a limitation. When a system becomes complex enough, it can begin to exhibit behavior that feels almost emergent. Not because there's anything hidden or intentional, but because the interactions between components create patterns that are not immediately obvious from the individual parts. The deep ocean, in this sense, might be less like a collection of separate processes and more like a continuous, dynamic system, one where small influences can propagate in subtle ways, shaping outcomes over time. And this brings us back to the earlier idea of coordination, or at least the appearance of it. Whether it's the timing of migrations, the distribution of bioluminescent signals, or the structure of chemical gradients, there are moments where the system seems to operate with a level of coherence that is difficult to fully explain through isolated mechanisms alone. Again, this doesn't imply anything beyond natural processes, but it does suggest that those processes may be more interconnected than we typically consider, that the boundaries we draw between biology and chemistry, between physics and ecology, might be more fluid in the deep ocean than they appear on the surface. And perhaps that's one of the quieter insights that begins to emerge as we explore this environment more carefully. Not that there is something hidden in the depths in a conventional sense, but that the depth itself, both literal and conceptual, allows for interactions that are harder to observe, harder to model, and therefore easier to overlook. So as we continue, we'll begin to narrow the focus again, turning towards specific case studies, individual discoveries, recorded anomalies, and the small details that have, over time, prompted researchers to pause, reconsider, and sometimes revise their assumptions. Because it's often in those specific moments, those brief instances where something doesn't quite match expectations, that the deeper patterns start to become visible. As we begin to focus more closely on specific observations, moments where researchers have paused, sometimes quietly, sometimes only briefly, we start to notice a pattern that isn't defined by any single discovery, but by the consistency of uncertainty itself. Not confusion, exactly, but a recurring sense that certain things in the deep ocean behave just slightly outside the boundaries of what we expect, even when we account for how little we've explored. One of the more interesting areas where this appears is in deep-sea encounters recorded by submersibles. Over the years, both manned missions and remotely operated vehicles have captured footage of organisms that don't immediately fit into known classifications. In many cases, these are eventually identified, new species, rare variations, or simply organisms observed in unusual conditions. That's part of the process. The ocean is vast, and biodiversity is still being catalogued. But not every observation reaches a clear resolution. There are recordings, sometimes only a few seconds long, where the shape, movement, or behavior of an organism doesn't align neatly with known patterns. It might be the way something moves, not quite like a fish, not quite like a jellyfish, or the way it interacts with light, absorbing or reflecting it in unexpected ways. The mainstream response to these observations is cautious, as it should be. Without sufficient data, it's difficult to draw conclusions. Lighting conditions can distort perception. Pressure can affect equipment. Even the presence of the submersible itself, its lights, its noise, can influence how organisms behave. But when similar types of ambiguity appear across different dives, in different regions, over extended periods of time, it becomes less about any single unexplained organism and more about the limitations of our current categories. It suggests that there may be forms of life, or at least forms of behavior, that don't fit comfortably within the frameworks we've developed so far. And this leads into another area that has quietly puzzled researchers: scale. In the deep ocean, estimating the size of an object or organism can be surprisingly difficult. Without clear reference points, something small can appear large, and something large can appear deceptively small. This is usually accounted for in analysis, but it introduces a level of uncertainty that doesn't exist in more familiar environments. There have been instances where sonar readings suggest the presence of large moving objects at depth, objects that are later attributed to known phenomena, like dense biological aggregations or unusual current interactions. And in many cases, that explanation holds. But what's interesting is how often the initial readings seem to imply something more structured, more defined, before being resolved into something more familiar. It raises a subtle question about interpretation. When we encounter something unexpected, how much of our initial reaction is shaped by incomplete data, and how much might reflect patterns we don't yet fully understand? Then there are the moments where equipment behaves in ways that are difficult to explain. Temporary signal losses, unexpected interference, readings that fluctuate without an obvious cause. These are usually attributed to environmental factors, pressure effects, electrical noise, or simple technical limitations. And again, that's reasonable. The deep ocean is an extreme environment, and equipment is pushed to its limits. But in some cases, these irregularities occur in clusters, multiple systems experiencing anomalies at roughly the same time, in the same general area. Individually, each incident can be explained. Collectively, they form a pattern that is harder to dismiss entirely. Not because it points to anything specific, but because it suggests that there may be environmental variables we're not fully accounting for. Factors that affect both biological systems and the tools we use to study them. One example that often comes up in discussions, though usually in a very measured way, is the recording of transient light phenomena at depth. Not bioluminescence in the typical sense, but brief, diffuse glows that don't seem to originate from a specific organism. These are rare and often difficult to verify, but they have been noted in multiple expeditions. The standard explanations include chemical reactions in the water, interactions between particles and light from the submersible, or even electrical effects within the equipment itself. And those explanations are plausible. But the fact that similar observations have been made under different conditions, with different equipment, keeps the question open, even if only slightly. And this is where the tone of deep ocean research becomes particularly important. There is a strong emphasis on restraint, on not over-interpreting limited data. That's what keeps the field grounded. But it also means that many of these small inconsistencies remain in the background, acknowledged but not fully explored until more evidence becomes available. Over time, as more dives are conducted and more data is collected, some of these uncertainties begin to resolve. Patterns become clearer, anomalies are explained, but others persist, not as dramatic mysteries, but as quiet gaps. Places where the data is just incomplete enough to prevent a definitive conclusion. And perhaps that's the most consistent pattern of all. Not any specific phenomenon, but the presence of these gaps across multiple areas of study. Biology, chemistry, physics, instrumentation, they all contain small areas where observation and explanation don't quite align. It doesn't mean there's anything hidden in a conventional sense, but it does suggest that the deep ocean operates at a level of complexity that we are still in the process of mapping out, both literally and conceptually. So as we move forward, the focus will shift once more toward the history of these observations, how they've been recorded, how interpretations have changed over time, and how certain ideas, once dismissed, later reconsidered, have shaped the way we think about the ocean today. Because sometimes, the most revealing insights don't come from a single discovery, but from watching how our understanding evolves, slowly, carefully, as new pieces of the puzzle come into view. When you begin to trace the history of deep ocean exploration, what stands out is not just how much we've learned, but how often our interpretations have shifted along the way. Ideas that once seemed unlikely, even implausible, have gradually become accepted, and others, once taken for granted, have been quietly revised or replaced. It's not a story of sudden breakthroughs, but of slow adjustment, of models being refined as new evidence appears, often in ways that challenge earlier assumptions. In the early days of oceanography, there was a prevailing belief that the deep ocean was largely lifeless. This wasn't an unreasonable conclusion at the time. Without sunlight, with immense pressure and near freezing temperatures, it seemed unlikely that complex organisms could survive, let alone form ecosystems. Early sampling methods, which were limited and often unreliable at great depths, appeared to support this view. Nets brought up little. Instruments returned sparse data. But as technology improved, that picture began to change. Life was found, first in small, scattered forms, then in more complex and abundant communities. Each discovery required a reassessment, not a complete rejection of previous knowledge, but an expansion of it. The deep ocean wasn't barren, it was simply difficult to observe. This pattern repeated itself with the discovery of hydrothermal vents. Before the late 1970s, the idea that entire ecosystems could exist independent of sunlight was not widely considered. When the first vent communities were observed, they didn't just add to our understanding, they forced a shift in how we think about the fundamental requirements for life. And yet, even after these major revisions, there remained smaller, quieter examples of reinterpretation. Observations that were initially set aside, only to be revisited later with new context. Data that didn't fit at the time, but began to make sense as models evolved. One subtle example comes from early sonar mapping. In its initial stages, sonar data was often difficult to interpret. Signals were noisy, resolution was limited, and unexpected readings were common. In some cases, these readings were dismissed as errors, artifacts of the equipment or the environment. But as sonar technology improved and similar patterns were observed repeatedly, some of those earlier errors were re-examined. Features that had once seemed anomalous were recognized as real structures, underwater mountains, ridges, or clusters of biological activity that had simply been beyond the resolution of earlier systems. This doesn't mean that all anomalies eventually become discoveries. Many do turn out to be errors or misinterpretations. But it does highlight an important aspect of the process. The line between noise and signal is not always clear, especially in environments where data is limited. And this is where the deep ocean presents a unique challenge. Because unlike many other fields of study, where experiments can be repeated under controlled conditions, deep ocean exploration is often constrained by access. Each dive is expensive, time-limited, and focused on specific objectives. There is less opportunity for continuous observation, for revisiting the same location under identical conditions. As a result, much of our understanding is built from snapshots, brief glimpses into environments that are otherwise out of reach. And when those snapshots contain something unexpected, it can be difficult to determine whether it represents a consistent feature or a one-time occurrence. Over time, as more data accumulates, patterns begin to emerge. But the process is gradual. It requires patience and a willingness to revisit earlier conclusions in light of new information. there are also cases where interpretations shift, not because of new data, but because of new perspectives. As scientific disciplines overlap, biology, chemistry, physics, geology, researchers begin to see connections that were not previously considered. A chemical anomaly might be linked to a biological process. A physical structure might influence ecological patterns. This kind of interdisciplinary thinking has led to some of the more nuanced insights in ocean science. It has revealed that the deep ocean is not just a collection of separate systems, but a network of interactions, where changes in one area can have subtle effects in another. And yet, even with these advances, there are still observations that remain difficult to place within existing frameworks, not because they contradict known science, but because they exist at the edges of it, where data is sparse and explanations are still developing. In some cases, these observations are revisited years later, when new technology or new methods allow for a clearer view. What once appeared ambiguous becomes more defined. In other cases, the ambiguity remains, not due to lack of effort, but because the conditions required to fully understand the phenomenon are difficult to reproduce. And this brings us back to a central idea that has been quietly building throughout this exploration. The deep ocean is not just a place where we lack information, it is a place where the process of gaining information is itself complex and evolving. So when we encounter something that doesn't quite fit, an unusual pattern, an unexplained signal, a structure that seems just slightly out of place, it's not necessarily an indication of something hidden or unknown in a dramatic sense. It may simply reflect the current limits of our observation, the boundaries of what we can measure and interpret. But those limits are not fixed. They shift over time, as tools improve, as models are refined, as perspectives change. And with each shift, some of the gaps in our understanding begin to close, while others, sometimes unexpectedly, become more visible. So as we move into the next part of this journey, we'll begin to explore a few specific cases, instances where observations have lingered at the edges of explanation, prompting continued study and quiet debate within the scientific community. Not because they offer definitive answers, but because they highlight the process itself. The way knowledge develops, adapts, and sometimes circles back on itself as new pieces come into view. As we begin to look at specific cases, individual moments where observation and explanation didn't immediately align, it becomes clear that the deep ocean doesn't present its uncertainties all at once. Instead, they appear in fragments. A sound here, a visual anomaly there, a reading that seems just slightly outside expected parameters. Each one, on its own, is often explainable or at least manageable within existing frameworks. But when viewed together, over time, they begin to form a pattern, not of something clearly defined, but of a system that consistently produces data at the edges of our understanding. One of the most well-known examples, often discussed in careful, measured terms, is a deep-sea acoustic event recorded in the late 20th century, informally referred to as the bloop. Detected by hydrophones designed to monitor underwater activity across vast distances, the sound was unusual because of its intensity and its frequency profile. It resembled, in some ways, biological sounds, low frequency, powerful, but it was far larger in scale than any known marine organism could reasonably produce. At the time, this raised a number of questions. Could it be a previously unknown species, a geological event, some kind of interaction between ice and water? The mainstream response was cautious, leaning toward natural explanations while acknowledging the uncertainty. Years later, with additional data and improved analysis, the sound was most likely attributed to ice quakes, large chunks of ice fracturing and shifting in Antarctic waters. The explanation fits the available evidence, and it aligns with other recorded sounds of similar origin. From a scientific standpoint, the case is considered largely resolved. But what makes it interesting isn't the final explanation. It's the process that led there. For a period of time, the data didn't fit neatly into known categories. It required further observation, comparison, and refinement of models. And during that time, it existed as a kind of open question, not because it was mysterious in a dramatic sense, but because it highlighted the limits of immediate interpretation. There are other examples, less widely known but similar in structure. Acoustic signals like the upsweep or Julia, recorded in different parts of the ocean, each with their own characteristics. In many cases, plausible explanations have been proposed: geological activity, underwater volcanic processes, ice movement. And yet, even with these explanations, there are often small aspects of the signals that remain less clearly defined: variations in timing, frequency shifts, patterns that don't fully repeat. Again, nothing that overturns our understanding, but enough to suggest that the processes generating these sounds are more complex than a single, simple cause. Then, there are visual cases, recordings from submersibles where something appears briefly in the frame, moves in an unfamiliar way, and then disappears. In most cases, these are attributed to known organisms viewed under unusual conditions. Lighting, angle, and motion can all combine to create impressions that don't match what we expect. But occasionally, the behavior itself is what stands out. Not the shape, but the movement, patterns that don't align with typical swimming motions, or interactions with the environment that seem slightly out of place. These are usually catalogued and set aside, not as evidence of anything extraordinary, but as data points that require more context. And that's the recurring theme: context. In the deep ocean, context is often incomplete. We see a moment, but not the conditions leading up to it or following it. We record a signal, but not the full range of variables influencing it. And without that context, interpretation becomes an exercise in probability rather than certainty. There are also cases involving physical structures, formations on the seafloor that appear unusually regular or patterned. In many instances, these are explained through known geological processes: sediment deposition, erosion by currents, chemical precipitation. Over time, these forces can create shapes that appear almost deliberate, even though they are entirely natural. But what's interesting is how our perception of these structures can shift depending on the level of detail we have. At lower resolution, a formation might appear smooth and uniform. At higher resolution, it reveals irregularities, variations that align with natural processes. Or sometimes, the opposite occurs. A structure that seemed irregular at first begins to show repeating patterns when examined more closely. This interplay between resolution and interpretation is a constant factor in deep ocean exploration. It reminds us that what we see is often a function of how clearly we're able to observe it. And when clarity is limited, our interpretations remain tentative. There's also a quieter category of cases, those involving environmental readings that fluctuate without an obvious cause. Sudden changes in temperature, pressure, or chemical composition that don't correspond to known events like currents or geological activity. These are often brief, sometimes isolated, and usually attributed to local variations that are not fully captured by the available data. But over time, as more sensors are deployed and more data is collected, some of these fluctuations begin to show patterns, not perfectly consistent, but recurring in similar forms across different regions. This suggests that there may be processes at work that are not yet fully integrated into our models, subtle interactions between physical, chemical, and biological systems that produce measurable effects. And once again, the response is careful. These patterns are noted, studied, compared. Hypotheses are proposed, tested where possible. But without continuous high-resolution data, conclusions remain provisional. So what we're left with is not a collection of unsolved mysteries in the dramatic sense, but a landscape of partial understanding. Areas where the data is just complete enough to reveal that something is happening, but not complete enough to fully explain it. And perhaps that's where the deep ocean becomes most compelling. Not because it hides clear answers, but because it consistently presents questions that are grounded, specific, and just slightly out of reach. As we move into the next part, we'll begin to explore how these kinds of observations influence the way scientists design future missions, how the presence of uncertainty shapes the questions we ask, the tools we build, and the places we choose to explore next. Because in a way, the unknown doesn't just exist in the ocean, it guides how we continue to study it. As these patterns of partial understanding begin to accumulate, acoustic signals that take time to explain, visual anomalies that resist immediate classification, environmental readings that fluctuate just outside expectation, they start to influence something less visible, but equally important, the way future exploration is designed. Because in a field like deep ocean research, uncertainty isn't just an obstacle, it becomes a guide. It shapes where scientists choose to look next, what tools they prioritize, and how they interpret the data they collect. At a practical level, this begins with mission planning. Every deep sea expedition is constrained by time, cost, and access. A research vessel can only remain at sea for so long. Submersibles can only dive a limited number of times. So decisions have to be made. Where to go, what to study, what questions to prioritize. The mainstream approach is to focus on areas with known significance. Hydrothermal vent systems, tectonic boundaries, regions with unusual biodiversity. These are places where previous research has already indicated something worth investigating. It's a logical strategy. Build on what you know, expand existing data sets, refine models. But increasingly, there is also attention given to areas that have produced ambiguous or unexpected data. Locations where previous readings didn't quite align with predictions. Regions where anomalies, however small, have been recorded more than once. Not because they suggest anything extraordinary, but because they represent gaps in understanding. And this is where the process becomes interesting, because designing a mission around uncertainty requires a different kind of thinking. Instead of testing a specific hypothesis, researchers often aim to gather broader data sets, high-resolution measurements across multiple variables, collected over longer periods of time. For example, instead of a single dive focused on visual observation, a mission might deploy a network of sensors, recording temperature, pressure, chemical composition, and acoustic signals continuously over weeks or months. The goal is not just to capture isolated events, but to build context, to see how different factors interact over time. This shift toward long-term observation reflects an important realization. Many deep ocean processes don't reveal themselves in short snapshots. They unfold slowly or intermittently, or in response to conditions that are not immediately obvious. And without continuous data, those processes remain fragmented, visible only in pieces. At the same time, there is ongoing development of new technologies designed to reduce the limitations we discussed earlier. Improvements in low-light imaging, for instance, aim to capture clearer visuals without relying as heavily on artificial illumination. Advances in autonomous underwater vehicles allow for longer missions without direct human control, increasing the range and duration of exploration. And then, there are efforts to improve data interpretation itself. Machine learning algorithms are being trained to recognize patterns in sonar data, to distinguish between noise and meaningful signals, to identify subtle correlations that might be missed through manual analysis. The mainstream expectation is that these tools will gradually reduce uncertainty, that with better data and better analysis, the gaps in our understanding will begin to close. And in many cases, that's already happening. Features that were once ambiguous are now clearly mapped. Organisms that were once unknown are now classified. But there's an interesting dynamic that emerges alongside this progress. As resolution improves, as datasets become more detailed, new layers of complexity often appear. Patterns that seem simple at lower resolution reveal additional structure. Variations that were previously invisible become measurable. It's a bit like increasing the magnification on a microscope. You don't just see more clearly, you see more to understand. And sometimes that leads to new questions rather than final answers. This dynamic influences not just how we explore, but how we think about exploration itself. There is a growing awareness that the deep ocean may not yield to a single, unified model. That instead of one comprehensive explanation, we may need multiple overlapping frameworks, each addressing different aspects of the system. For example, a biological pattern might be explained through ecological interactions at one level, but also influenced by chemical gradients or physical forces at another. A geological structure might be shaped by tectonic activity, but also modified by biological processes over time. And when these layers interact, the result can be behavior that appears more complex than any single explanation can fully capture. So rather than trying to simplify the system, there is a gradual shift toward embracing that complexity, toward building models that can accommodate variation, uncertainty, and the possibility of incomplete data. This doesn't mean abandoning precision or rigor. On the contrary, it requires even more careful measurement, more detailed analysis. But it also requires a certain flexibility in interpretation, a willingness to adjust models as new information becomes available, without assuming that the current framework is final. And perhaps that's one of the quieter lessons emerging from deep ocean research. Not that the unknown is something to be eliminated, but that it is an inherent part of studying systems at this scale. That uncertainty, when approached carefully, can actually guide discovery rather than hinder it. So as we continue, we'll begin to explore how these evolving methods and perspectives might shape the future of deep ocean exploration. What kinds of questions are scientists starting to ask now that weren't considered before? What kinds of environments are being prioritized, and why? Because the direction of future research often tells us as much about what we don't understand as the data we've already collected. And in a place as vast and as quietly complex as the deep ocean, that direction is still unfolding. Slowly, carefully, one observation at a time. As the direction of deep ocean research continues to evolve, something subtle begins to shift, not just in the tools being used or the locations being explored, but in the types of questions being asked. Earlier, much of oceanography focused on mapping, cataloging, and identifying. What is there? How deep is it? What lives in this region? These were the foundational questions, and they were necessary. But now, as more data accumulates, the focus is gradually turning towards something more complex. How these systems behave over time, and how different layers of the ocean might be influencing each other in ways that aren't immediately obvious. One area where this shift is particularly noticeable is in the study of deep ocean connectivity. Not connectivity in a simple physical sense, currents moving water from one place to another, but in terms of how events in one region might subtly affect conditions in another, sometimes across vast distances and long periods of time. The mainstream explanation acknowledges that the ocean is a global system. Currents circulate water around the planet, distributing heat, nutrients, and dissolved gases. This circulation is driven by differences in temperature and salinity, forming what's often described as the thermohaline circulation. It's a slow process, but a powerful one, linking surface waters to the deepest layers of the ocean. But when scientists look more closely at certain patterns, such as synchronized changes in chemical composition across distant regions, or simultaneous shifts in biological activity that don't appear to be directly connected, they begin to consider whether there are additional layers of interaction at play. These observations are subtle. They don't contradict existing models, but they don't always fit neatly within them either. For example, there have been instances where deep-sea ecosystems in separate locations show changes in population or behavior over similar timeframes, even when those locations are not obviously connected by known current pathways. The standard interpretation is that these are responses to broader environmental changes, perhaps shifts in global climate patterns, variations in surface productivity, or changes in ocean chemistry that propagate through the system over time. And that explanation is likely correct in many cases. But what makes it interesting is the timing. In some instances, the changes appear to occur more rapidly or more synchronously than models would predict based on the known speed of deep ocean circulation. It suggests that there may be mechanisms of influence, whether physical, chemical, or even biological, that operate on timescales or pathways we don't fully understand yet. And this leads into another emerging area of research: the role of signals in the deep ocean. Not signals in the sense of communication as we typically think of it, but in terms of how information, environmental information, is transmitted through the system. For instance, pressure waves, temperature shifts, chemical gradients, these can all carry information. They can influence how organisms behave, how ecosystems respond, how processes unfold over time. In a highly connected system, even small changes can propagate, creating effects that appear distant from their origin. The mainstream view treats these as physical processes, governed by known laws of fluid dynamics and thermodynamics. And again, that's accurate. But when these processes interact, when pressure changes influence chemical reactions, which in turn affect biological activity, the system begins to exhibit behavior that is more complex than any single layer alone. This is where the idea of emergent behavior becomes more relevant, not as something mysterious, but as a natural consequence of complexity. When enough variables interact, patterns can arise that are not immediately predictable from the individual components. In the deep ocean, where observation is limited and data is often fragmented, these emergent patterns can be difficult to detect. They may only become visible when data from multiple sources, acoustic, chemical, biological, is combined and analyzed over long periods. And even then, interpretation remains cautious. Scientists look for repeatability, for consistency across data sets. They test whether a pattern holds under different conditions, whether it can be explained through known mechanisms, and in many cases it can. But occasionally, there are patterns that persist without a clear, singular explanation. Not because they defy understanding, but because they exist at the intersection of multiple processes, each contributing in subtle ways. Then there's the question of boundaries. In earlier models, the ocean is often divided into layers or zones, each with its own characteristics. And this is useful. It helps organize our understanding. But in reality, these boundaries are not fixed. They shift, they overlap, they blur. Water masses mix, currents intersect, chemical gradients change over time. And as a result, the behavior of the ocean doesn't always conform to the neat divisions we impose on it. This has led to a growing interest in transitional zones, areas where different layers interact. These regions can be more dynamic, more variable, and sometimes more difficult to model. But they may also hold important clues about how the system operates as a whole. Because if the deep ocean is not just a collection of separate zones, but a continuous interacting system, then understanding those interactions becomes key. And this brings us back to a familiar idea, now seen from a slightly different angle. The deep ocean is not simply unknown because we haven't explored it fully. It is also complex in a way that resists simple categorization. The more we learn, the more we see how interconnected its processes are. So as we continue, the focus will begin to shift once more toward the implications of this complexity, not in terms of dramatic conclusions, but in terms of how it changes our perspective, how it influences the way we think about exploration, about knowledge, and about the limits of what we can reasonably expect to understand in a system of this scale. Because sometimes, the most meaningful insight is not a specific discovery, but a change in how we frame the questions themselves. As this perspective begins to settle in, that the deep ocean is not just vast, but deeply interconnected and layered in ways that resist simple explanation, it naturally leads to a quieter, more reflective question. Not just what we are discovering, but how close we are to the limits of what we can discover, at least with the methods and assumptions we currently rely on. Because every system we study, no matter how complex, is approached through a framework. We define variables, we build models, we test predictions. And for many environments, that approach works remarkably well. Patterns stabilize, uncertainties shrink, and over time, a coherent picture emerges. But the deep ocean seems to behave differently, not in a way that breaks those methods, but in a way that continually stretches them. One reason for this may simply be scale. The ocean covers more than 70% of the Earth's surface, and its depth adds an entire dimension that is difficult to fully grasp. But beyond physical scale, there is also informational scale. The number of interacting variables, the range of timescales, the layers of feedback that exist between biological, chemical, and physical processes. The mainstream view acknowledges this complexity, and much of modern oceanography is built around managing it, using computational models, long-term data sets, and increasingly sophisticated tools to track changes over time. These models have become more accurate, more detailed, and more predictive. And yet, even with these advances, there are moments where predictions diverge slightly from observation. Not dramatically, but consistently enough to remind us that the system is not fully captured. A current behaves differently than expected. A chemical gradient shifts without a clear cause. A biological response occurs earlier or later than models would suggest. Each of these differences is usually small. Each can often be explained by adjusting parameters, refining inputs, or accounting for local variability. But taken together, they suggest that there may be aspects of the system that are not yet fully represented in our models, not because they are unknowable, but because they are difficult to isolate and measure directly. This leads into an interesting idea that is beginning to appear more frequently in scientific discussions: the concept of observational limits. The recognition that in certain environments, especially those that are difficult to access, there may be a threshold beyond which additional detail becomes increasingly difficult to obtain, not just technologically, but conceptually. In the deep ocean, this limit is shaped by multiple factors: the difficulty of sustained observation, the reliance on indirect measurement, the timescales over which processes occur, and perhaps most importantly, the way in which different processes overlap and interact. For example, if a chemical change is observed at a certain depth, it may be influenced by biological activity, geological input, and physical mixing, all at once. Separating those influences requires data that is not only precise, but continuous and multidimensional. And even then, interpretation remains complex. The mainstream response to this challenge is to improve resolution, to gather more data from more sources over longer periods of time. And this approach has been effective. It has revealed patterns that were previously invisible, clarified relationships that were once uncertain. But there is also a recognition that increasing resolution does not always simplify the system. Sometimes it reveals additional layers of complexity, new variables, new interactions, new sources of variability. And this is where the perspective begins to shift again, from trying to fully resolve the system to understanding how to work within its complexity, to identify which patterns are stable, which are variable, and which may never be fully predictable. This doesn't mean accepting uncertainty as a limitation, but rather as a characteristic of the system itself, a feature, not a flaw. And in that sense, the deep ocean becomes less like a puzzle to be solved and more like a process to be observed, something that can be understood in parts, in layers, but perhaps not in its entirety at any single moment. There's also an interesting parallel here with other areas of science. In fields like climate modeling or astrophysics, researchers often deal with systems that are too large, too complex, or too distant to observe directly in full detail. In those cases, understanding comes from combining observation with inference, building models that are not perfect but useful. The deep ocean may require a similar approach, not a single unified explanation, but a set of overlapping models, each capturing a different aspect of the system. Together, they provide a working understanding, even if some details remain unresolved. And perhaps that's where the deeper insight lies, not in uncovering a hidden layer that explains everything, but in recognizing that some environments, by their very nature, invite ongoing exploration rather than final answers. So as we move into the next part, we'll begin to explore what this means in a broader sense, not just for oceanography, but for how we approach the unknown more generally, how we balance certainty and curiosity, how we decide which questions to pursue, and how we interpret the answers we receive. Because in the end, the deep ocean is not just a place we study, it's a reflection of how we study anything that lies beyond immediate reach. As we continue forward, the focus begins to shift again, but this time in a way that feels less about the ocean itself and more about the mindset we bring to it. Because after looking at the structure, the chemistry, the anomalies, and the limits of observation, a quieter realization starts to take shape. That the deep ocean is not just a physical environment, but also a kind of boundary for human understanding. Not a hard limit, but a moving one, defined by how we ask questions, how we interpret uncertainty, and how willing we are to adjust our perspective when the data doesn't fully align. In most areas of science, there is an expectation, sometimes unspoken, that with enough time, enough data, and the right tools, uncertainty will gradually disappear. That what is unknown will become known, and what is unclear will eventually resolve into something precise and predictable. And to a large extent, that expectation has been justified. It's how we've mapped continents, decoded DNA, and understood the motion of planets. But the deep ocean seems to resist that trajectory, at least in a subtle way, not by withholding information, but by presenting it in forms that are layered, incomplete, and often dependent on context that is difficult to capture all at once. It's not that answers don't exist, it's that they don't always appear in isolation. They are embedded in systems that are constantly changing, interacting, and evolving. And this is where the approach becomes just as important as the data itself. Because when faced with a system like this, there are two general ways to respond. One is to narrow the focus, to isolate variables, simplify conditions, and aim for precise, controlled understanding. The other is to broaden the perspective, to look at patterns across multiple layers, to accept a degree of uncertainty, and to build understanding gradually, through accumulation rather than isolation. In deep ocean research, both approaches are used. But increasingly, there is a recognition that the second approach, this broader, more integrative way of thinking, may be necessary to fully appreciate what's happening beneath the surface. This doesn't mean abandoning rigor or precision. It means applying them in a way that acknowledges complexity rather than trying to eliminate it entirely. It means being comfortable with partial answers, with models that are useful but not complete, with observations that raise new questions instead of closing existing ones. And in that sense, the deep ocean becomes a kind of training ground for a different kind of thinking, one that is less about reaching final conclusions and more about refining the process of inquiry itself. There's also something else that begins to emerge when you look at it this way, a sense that many of the inconsistencies we've discussed, the small mismatches between observation and expectation, are not necessarily problems to be solved, but signals to be interpreted, indicators that there is more happening within the system than we currently account for. For example, when a migration pattern doesn't align perfectly with light cycles, it may not mean that the model is wrong. It may mean that there are additional variables influencing behavior, variables that are subtle, distributed, or only active under certain conditions. When a chemical reading differs slightly from predictions, it may not indicate an error. It may reflect an interaction between processes that we've only partially understood. And when an anomaly appears in a recording, a sound, a shape, a movement that doesn't quite fit, it may not require an immediate explanation. It may simply need to be placed within a larger context, where its significance can be evaluated over time. This way of thinking requires patience. It requires a willingness to let data accumulate, to revisit observations, to allow patterns to emerge gradually, rather than forcing them into predefined categories. And perhaps that's one of the more understated aspects of deep ocean research. It is, by necessity, a slow science. Not just because of the logistical challenges, but because the environment itself operates on timescales and levels of complexity that resist quick interpretation. So as we continue toward the final parts of this exploration, the focus will begin to settle, not on individual phenomena, but on the broader implications of everything we've looked at so far. What does it mean to study a system that is both vast and partially inaccessible? How do we balance confidence in what we know with openness to what we don't? Because in the end, the deep ocean may not reveal its structure all at once. It may never present a complete picture in the way we might expect, but it does offer something else, a continuous opportunity to refine how we observe, how we question, and how we understand the world around us. And in that quiet, ongoing process, there is a kind of clarity, not the clarity of having all the answers, but the clarity of knowing how to keep looking. As we begin to approach the final stretch of this exploration, there's a natural tendency to try and gather everything we've considered so far into something more defined, to ask, in a quiet way, what it all adds up to. But the deeper we've gone, the more it becomes clear that the deep ocean doesn't lend itself to simple conclusions. Not because it's unknowable, but because what it offers is less like a single answer and more like a shift in perspective, something that changes how we think rather than what we think. Throughout this journey, we've moved from structure to chemistry, from observation to interpretation, from isolated anomalies to broader patterns. And at each step, the same subtle theme has reappeared. Not contradiction, but incompleteness. Not mystery in a dramatic sense, but a quiet, consistent presence of gaps, places where what we observe and how we explain it don't fully align, at least not yet. The mainstream scientific framework remains strong. it explains the vast majority of what we see. Ocean currents, pressure dynamics, biological adaptation, chemical cycles, these are well understood, supported by decades of research and evidence. There's no need to replace that framework, and no indication that it's fundamentally flawed. But within that framework, there is room, small, carefully defined space for uncertainty, for the recognition that even well-established systems can contain details that are still being resolved. And it's within that space that the deep ocean becomes most interesting. Because when you look at it closely, the ocean doesn't just contain unknowns, it produces them consistently in ways that are measurable, repeatable, and grounded in observation. Slight variations in expected patterns, signals that take time to interpret, structures that invite multiple explanations before settling into one that fits best. And over time, as we've seen, many of these unknowns are resolved. They become part of the broader understanding. But the process itself doesn't stop. New data introduces new variations, new questions, new edges to the map. So instead of thinking of the deep ocean as something that will eventually be fully understood, it may be more accurate to think of it as something that will be increasingly understood, without ever becoming completely fixed in a final form. There's also something else that emerges when you take a step back, a sense that much of what we've been examining, the inconsistencies, the patterns at the edge of explanation, are not isolated to the ocean. They appear in other complex systems as well: climate, ecosystems, even certain areas of physics, places where scale, interaction, and limited observation create conditions where knowledge develops gradually and sometimes unevenly. And in those systems, the goal is not to eliminate uncertainty entirely, but to understand its structure, to know where it exists, how it behaves, and how it influences the conclusions we draw. In that sense, the deep ocean becomes more than just an environment to study. It becomes a reference point, a way of understanding how we approach complexity itself, how we balance confidence with caution, how we refine models without assuming they are complete, how we remain open to revision without losing grounding. And perhaps that's why the ocean continues to hold such a quiet pull on the imagination. Not because it promises hidden answers, but because it reflects something fundamental about the process of discovery. The idea that knowledge is not a destination, but a continuous movement, shaped by observation, adjusted by evidence, and always, in some small way, incomplete. So as we move into the final part, the focus will narrow one last time, not toward a conclusion in the traditional sense, but toward a kind of stillness, a moment to consider what it means to explore something that may never be fully mapped, and what that says about the nature of understanding itself. Because sometimes, the most meaningful insight is not what we find, but how we learn to keep looking. As we settle into this final stretch, there's a natural quietness that begins to take over, not just in the tone of the ocean itself, but in the way we think about everything we've explored. Because after moving through layers of structure, chemistry, observation, uncertainty, and evolving understanding, what remains isn't a single conclusion. It's a perspective that feels more stable precisely because it doesn't try to force one. The deep ocean, in many ways, has revealed itself not as a place of answers waiting to be uncovered, but as a system that continuously reshapes the questions we ask. And that distinction matters, because it changes the role of exploration from something that seeks to finish a map into something that gradually refines it, knowing that the edges will always extend a little further. If you think about it carefully, almost every area we've touched on carries this same underlying structure. We observe something, movement, sound, a pattern in data. We build an explanation based on what we know. And then, over time, We either confirm that explanation or adjust it as new information comes in. Most of the time, the process is smooth, incremental, quiet. But in the deep ocean, that process feels more visible. The gaps are easier to notice. The transitions between uncertainty and understanding are more gradual, more deliberate. And because of that, it becomes easier to see how knowledge itself is built, not as a fixed structure, but as something that adapts. There's also a kind of balance that begins to emerge between confidence and curiosity. On one side, we have a vast body of established science, models that work, explanations that are consistent, predictions that are reliable within known conditions. On the other side, we have these small, persistent edges where the system behaves in ways that are just slightly more complex than expected. And instead of one side replacing the other, they coexist. The known provides structure, the unknown provides direction. This balance is what allows exploration to continue without becoming either rigid or speculative. It keeps the process grounded but open, focused but flexible. And perhaps that's one of the more important things to take from all of this. Not any specific phenomenon, not any individual anomaly, but the way in which they collectively shape how we approach something as vast and layered as the deep ocean. Because when you remove the expectation of final answers, something interesting happens. The need to resolve everything immediately begins to fade. In its place, there's a different kind of clarity. One that comes from understanding how much we already know, while recognizing how much remains to be explored. And in that space, the deep ocean becomes less about mystery and more about continuity. A system that is always in motion, always interacting, always presenting new details as our ability to observe improves. Even the idea of unexplored begins to shift slightly. It no longer means completely unknown. It means partially observed, partially understood. A place where each new piece of data adds to a structure that is already forming, even if it's not yet complete. So rather than imagining the deep ocean as something waiting to be revealed all at once, it may be more accurate to think of it as something that is gradually coming into focus. Not uniformly, not all at the same time, but in layers, each one adding depth to the overall picture. And that picture, even in its current form, is already remarkably detailed. We understand the major currents, the general structure of ecosystems, the fundamental processes that sustain life at extreme depths. We've mapped significant portions of the seafloor, identified thousands of species, and developed models that explain a wide range of observed behavior. But alongside that detail, there is still room for refinement, for small adjustments, new connections, deeper insights. And that ongoing process is what keeps the field active, evolving, quietly moving forward. So as we prepare to close this exploration, there's no need to draw a firm line around what we've covered. No need to define a final answer. Because the deep ocean doesn't really offer that kind of ending. Instead, it offers something more subtle. A reminder that understanding is something that develops over time, through careful observation and thoughtful interpretation. That even in the most well-studied systems, there are always layers that can be examined more closely. And perhaps most importantly, it offers a kind of stillness, not the absence of activity, but the absence of urgency. The sense that it's okay not to resolve everything at once, that there is value in simply observing, in noticing patterns, in allowing ideas to develop gradually. Because sometimes, the most meaningful progress doesn't come from reaching a conclusion, but from continuing to look, with just a little more clarity than before. As we come to the final part of this journey, there's a quiet sense of returning. Not to where we started, but to the feeling that first drew us in. That awareness of the ocean at night, stretching out beyond what we can see, holding more depth than we can easily imagine. And after everything we've explored, the layers, the patterns, the uncertainties, that feeling hasn't disappeared. If anything, it's become more grounded, more defined, and at the same time, more open. Because what the deep ocean ultimately reveals is not a hidden answer waiting at the bottom, but a process unfolding across scale, time, and perception. A system that is vast enough to contain both what we understand and what we are still in the process of understanding, without contradiction. And within that system, the line between known and unknown is not fixed. It moves slowly as observation improves and interpretation evolves. At the beginning, we considered the idea that the ocean exists somewhere between fact and the unknown. And now, at the end, that idea feels less like a mystery and more like a natural state, not just for the ocean, but for any complex system. The difference is that in the deep ocean, that state is easier to notice. The gaps are more visible, the transitions more gradual, the process of understanding more transparent. We've seen how patterns emerge, not as definitive answers, but as signals. Subtle inconsistencies in migration, variations in chemical composition, acoustic phenomena that take time to interpret, structures that invite multiple explanations before settling into one that fits best. None of these, on their own, redefine what we know. But together, they create a picture of a system that is continuously refining itself in our understanding. And importantly, the mainstream explanations remain central throughout all of this. They provide the structure, the foundation. Without them, there would be no framework to recognize these patterns in the first place. But alongside that structure, there is space, carefully maintained, for observation that doesn't immediately resolve, for data that takes time to integrate, for questions that remain open just long enough to guide further exploration. That balance is what keeps the entire process grounded. It allows curiosity to exist without becoming speculation, and it allows uncertainty to exist without undermining what we already know. There's also something else that becomes clear when you step back one last time. The deep ocean does not need to be fully explored to be meaningful. It doesn't need to reveal everything at once to be understood in a useful way. Its value, in a sense, comes from the way it continues to engage the process of discovery. Every new dive, every new data set, every refined model adds to a structure that is already in motion. And while that structure may never be complete in the way we might expect, it becomes increasingly coherent over time. So instead of imagining a future where the ocean is fully mapped, fully explained, and entirely known, it may be more accurate to imagine a future where our understanding becomes deeper, more detailed, and more interconnected, without losing the sense of openness that makes exploration possible. And that brings us back, quietly, to where we began, to the idea of looking out over the ocean, knowing that beneath the surface lies something vast, structured, and still unfolding. Not something hidden in a dramatic sense, but something that invites continued attention. Because in the end, the deep ocean doesn't ask us to solve it. It asks us to observe it carefully, to think about it clearly, and to accept that understanding, like the ocean itself, has depth. And maybe that's why it remains one of the most compelling places we can study. Not because of what it might be hiding, but because of how it changes the way we look. And with that, we reach the end of this exploration. Not as a conclusion, but as a pause in a process that continues, far below the surface, whether we are watching or not.